fatty acid analysis, stable isotopes, and then we look at stomach contents. You go down. So Otsego Lake is located about an hour west of Albany, right there. It's about 7.8 miles long with an average depth of 82 feet and a max depth of 162 feet. The common species include lake trout, black bass, rainbow smelt, yellow perch, and walleye. But the primary fish that the lake is managed for is lake trout. They've been stocked annually since 1950, with current stockings approximating about 2,500 yearlings in recent years, which is pictured by this top one here. They're about 200 millimeters in length. Adults generally fall into two size categories in this lake. Your smaller adults, which can be between 500 and 700 millimeters, and your larger adults, which can be greater than 900 millimeters. Both of these fish pictured here are held by the same person, so you can see the difference by the size of the hands there. So these are the two main size categories in the lake. We're missing a lot of smaller fish, we're missing a lot of those middle-sized fish. But these adults are generally considered to be the top predators in the lake. But despite that, their diet has been recently poorly understood. Otsego Lake has had, as many of the lakes in New York, has had a history of introduced and invasive species with records dating back to 1925. As I go through this, I want you to follow the lake trout graph here, followed by the triangles. I know it's a little bit of a cluttered graph, but I'll get there. So starting in sometime between 1925 and 1942, Cisco were accidentally stocked into the lake when they were intending to stock lake whitefish. These quickly became the top planktivores in the lake, which were then subsequently replaced in 1979 by rainbow smelt as the top planktivores, which were then replaced by alewife in 1986 as the top planktivores. And during this time period of when alewife were in the lake, you can see this, the lake trout population steadily rising and reaching its peak. But starting in 1998, walleye were beginning to stock in the lake. To manage the alewife populations became greater and greater in biomass. And then after 2007, when zebra mussels were introduced in the lake and started controlling the plankton population a bit more, the alewife population finally crashed by 2012. That was the last reported sighting of an alewife. So during this time period, you can see, as I mentioned, that the lake trout population is reaching its peak and then slowly falling down afterwards. So while they were in the lake trout were consuming these fish as their main source of their diet. So we have a before alewife diet analysis, we have the during alewife diet analysis, and we're missing this after. So the before alewife, they were consuming mainly sculpin and chironomids, with lake trout, cisco, and yellow perch each being found in one stomach each. After alewife were introduced, you can see the alewife quickly spiked up to 78.9% of the diet, with 2.1% being chironomids, and then slimy sculpin falling down to just being found in one stomach, as well as creek chub and largemouth bass also in one stomach each. So that was the before, this is the then, now we're going to the now. So the purpose of this talk, as I mentioned earlier, was to determine what this now is. This symposium is on the then and now. I like to refer to this as the then, and now. So we're trying to determine what the current diet is using 3 different analyses. The reason why we're using 3 different analyses is because each analysis has their own costs and benefits. For instance, as I pictured here, stomach content reflects diet over a short period of time, about 24 hours. Fatty acid analysis can reflect diet over a couple of weeks to months, and stable isotope analysis can reflect diet over a few months. So using multiple analyses can really cover your bases and provide a more holistic picture of the food web and what the fish are eating. And it can prevent you from either overestimating or underestimating the contribution of the diet. So getting into my methods, lake trout were sampled using trap nets and gill nets during the fall of 2021 and the fall of 22. Prey fish, including but not limited to rainbow smelt, yellow perch, black bass, and slimy sculpin, were collected using boat and backpack electrofishing during the spring, fall of 2021 and the spring, summer, and fall of 2022. And these fish were limited to those of consumable size by lake trout, so we didn't want to get fish that were too big, because if the lake trout aren't eating them, there's no point in looking at them. Due to the possibility of cannibalism of stocked lake trout, we also collected some of the stocked lake trout from the spring of 2022 before they were released into the lake. And then we also looked at macroinvertebrates with sampling being performed with an Ekman sediment sampler during spring, summer, and fall of 2022, which occurred at the same time as the crayfish collections. So we took 3 different parts from each lake trout. We took the stomachs to look at the stomach contents. We took the belly flap to look at fatty acid analysis, and we took dorsal muscle for stable isotope analysis. These latter 2 tissues have been shown to be the best indicators of their respective analyses. Crayfish were kept as a whole body under the assumption that they would be consumed whole in the lake, and macroinvertebrates were aggregated by lowest taxonomic level, just so we could get up to our required sampling weight for our tracers. So stomach contents were identified to the lowest possible taxonomic level, with their prey contribution being determined using wet weight and frequency of occurrence across all stomachs. Lipids were measured gravimetrically, and fatty acids were quantified using gas chromatographer mass spectrometer. Stable isotopes samples were prepared at SUNY Brockport and shipped to UC Davis for analysis, where they used quantified carbon-13 and nitrogen-15 using a elemental analyzer with a mass spectrometer. So getting into my preliminary results, I'm only going to be talking about my first collection of lake trout and the subsequent spring and summer collections of prey, because these are the data sets that we have fully analyzed and I can tell you the most about. So moving into my stomach analysis, the yellow perch were overwhelmingly shown to be the main contributor to the diet, as you can see by this orange graph here. With chironomids, scuds, and sunfish falling at lower levels. But we can see that by the blue graphs, by the frequency of occurrence, each of these species only occurred in one stomach each, with the majority of the diet coming from one fish that had all of these fish, and half the lake trout eggs, and one of the mayflies. So this analysis is great because you can look at what is specifically in the stomach, and there's no ambiguity. This is what this fish is eating. But it does provide some bias in that one fish can overwhelmingly dictate what your analysis is showing, which is why I mentioned that we looked at 3 different analyses. So moving into our fatty acid analysis, the fatty acid analysis operates under the assumption that you are what you eat. So fatty acids are passed conservatively from the prey to the predator. So the predator will have a fatty acid signature that is similar to the prey that they are consuming. So as I move through the next 2 graphs, I want to point out that these are ordination plots. So those points that are more closely joined together are more similar to each other. Those that are farther apart are more dissimilar. So on this graph, you can see that the rainbow smelt pictured here and the yellow perch here are more similar to each other than, say, the smallmouth bass, rock bass and smallmouth bass here. So these 2 groups are more similar to each other than they are to one another. With each of these vectors indicating the fatty acid that is contributing to most of the differentiation between the different species. So a requirement of fatty acid analysis that the fatty acid signatures of the prey have to be distinct from one another. So our results showed that in these are only a few of the species that we looked at. The graph gets a little too cluttered if I put them all up there. We looked at 26 different prey species. These are just some of the considered more common and appropriate ones. So the prey species were all fatty acid signatures were distinct among all prey. So that allows us to use this analysis. So when we added our lake trout here, we can see that the lake trout are characterized by high levels of 21 and 22, 5, and 3. So these are the fatty acids that are characterizing your lake trout populations. So when we look at that, we can see that the slimy sculpin and the stocked lake trout fall in places of importance, characterized by these same two fatty acids. So this indicates that these are the prey being consumed, and this is reflective of this analysis. Moving into the stable isotopes, we can plot the carbon and nitrogen levels and look at their trophic position and where they're getting their carbon source from. We can see that the stocked lake trout kind of fall off to the side, which in normal instances would indicate that they're getting their food from a more benthic environment within the lake. But because these fish were taken right off the hatchery truck, it's more reflective of them eating a completely different diet because they're getting the hatchery feed. And then as we can see, the lake trout, as expected, fall at your top predator position with slimy scallop and rainbow smelt, and falling next, and then so on and so forth down to the macroinvertebrates at the bottom. I might point out that the yellow perch are a little bit lower than you might expect, but I'd like to remind you that all these are consumable size, so they're all smaller than you might expect. For adults, while these rainbow smelt and slimy sculpin, because they are smaller fish by nature, are going to be adults when they're in this analysis. So moving into the specific numbers associated with this, we used two-source Bayesian mixing models to estimate the prey contribution, and this analysis was performed with 3 million permutations with all Gell-Mann diagnostics falling below 1.05, and all this means is that the prey were well represented and reflected in my analysis. And then based on this, the lake trout are likely consuming 28.7% slimy sculpin, 24.2% rainbow smelt, and 16.2% bluegill. So I know I just threw a lot of analyses at you and a lot of numbers. We're going to go through it a little bit slowly, or a little bit more specifically. So the top prey that we were collecting for stomach content was yellow perch, sunfish, and lake trout eggs. The top fatty acid analysis, or the fatty acid analysis, showed slimy sculpin and juvenile yellow lake trout being reflected as the diet source for that analysis, and slimy sculpin, rainbow smelt, and bluegill were reflective of stable isotope analysis. So we collected our fish in the fall off of their spawning reefs. So stomach content analysis is going to show a more fall-oriented diet. It's what's on the reefs while they're there. The middle ground is going to show some middle ground between when they're in their deep water and when they're near shore. So we have slimy sculpin and juvenile lake trout. And your stable isotope analysis over your longer term is going to show more of the deep water fish. So your slimy sculpin, rainbow smelt, and then bluegill is a little bit closer. So when we combine all of these analyses, we get these as our top species being reflected. Slimy sculpin, yellow perch, sunfish, rainbow smelt, and juvenile lake trout. And with that, I'd like to thank I'd like to thank my committee, Dr. John Conchard, Scott Wells, and Dr. Matt Altenritter for their assistance, as well as students from SUNY Brockport for their help with analyses and collections. Really couldn't do it without you guys. As well as faculty, staff, and students from SUNY's Cobleskill and Oneonta for graciously allowing us to steal your boat, as well as some of your other gear so that we didn't have to track across New York with all of our stuff, as well as staff from New York DEC's Region 4 for the same thing. my life so much easier. This project was funded by St. Rockport's Distinguished Professors Award, the Department of Environmental Science and Ecology, and the Great Lakes Research Consortium. And travel support for this was provided through the New York chapter of American Fisheries Society, Clement Spindler Student Travel Award. And that, thank you for your attention.